Hello everyone. Today is Codeforces round 126 educational and it's already started. So problem A, you are given two arrays of length n. You can perform the following operation any number of times. Choose integer index I, swap ai and bi, okay? Possible sum you can achieve after performing several possibly zero operations. Okay. Well, it's if both of them are sorted, right? Or something like that. So we have two arrays. Here it's 0. In the second case it's 1, 2, 3, 4, 5. I don't think we need to change it. Did that all. A5 and B5. Two, 4, 5, and 1, 2, 3, 4, 5. Swap these two. So it's the sum of differences of all adjacent elements. Oh, there aren't that many. There are 25 elements. But still, that's... I can swap each pair or not, but that's not fast enough. 2 to the 25th is... and that's 4,000 times. So that's not good. Here, why is that the best? You are given two arrays and you can perform the... Oh, I can only swap elements that are above each other. Oh, okay. Well, in that case... I'll try to make one of them increasing. Yeah, for each pair I just calculate whether it's this plus this or the other way around. Wait, it's that. I think I'm overthinking this, but I can do it with a dp. Yeah, let's put it right. dp, and I have I have dpi 0 equals best if I is not swap So what am I doing exactly? Each two numbers, So for each pair of numbers, I can either swap the last two, and then I'll take the sum of the last two if the last two have been swapped plus this difference. If the last two have been swapped, then I'll swap these two. No, I think I can just take the minimum of, yeah. And it can be 20 times that, it needs to be long. 0 or int I equals 0 and smaller than plus I, and smaller than n minus 1. Minimum of ai minus ai plus 1 bi minus bi plus 1, and yeah, I think that works, but I'll submit it here. I'm just submitting it on my second monitor. Okay, it got accepted. Yeah, that will be tricky to explain why that works. Okay. What's 32,768? Yeah, that's 2 to the 15th. Okay, 2 to the 15th. We evaporate one operation, you can set increase it or multiply it by 2. What is you need to make all ai equal to 0. I bring it to the nearest power of 2 and then I multiply it by 2 until I get 32,000. Yeah, that's definitely true. So let's take a look for 49. 49 we need to bring it to 64. 64 minus 59, that's 15. But no. I can either bring it to the closest power of 2 and then multiply it by 2 until I get to 10 to the 2 to the 15th, right? 2 to the 15th. Or I multiply it by 2, then bring it to the closest, then multiply it by 2 until I get 2 to the 15th. Okay. And that's gonna be like very logarithmic. Okay. Yeah, and when I'm duplicating, I'm just bringing it over to my second monitor, because then I look at it in one code. I think that works. Okay, I have. don't actually need to store it, right? And then what I do is, I think I can just print that. So y will x smaller than n should be 2, and I need to do, wait, let's just print out n while x is smaller than n. I need to make like some powers of 2 vector. And then I have and it's x plus and I'll that's not necessarily correct. There's some off by 1 error for sure. What's the problem? I need to multiply 2. Okay, so that needs to be up to 15. 19, the next power is 32. And from 32, how many times do I need to 2 to the 11 times 32? I need to do that minus 1. That's it minus 1. There's the off by 1 error I was referring to. And now hmm. 32 minus 19 plus 10. That's 23 moves. Okay, I might be completely wrong. I have 28. Okay, let's think about this again because I think I'm completely wrong on my solution. Right. Oh, it's always I just look at the largest power of 2 that's in it and okay, oh god, I'm stupid. That's much easier. So it's definitely gonna work in 15 moves. And what I do is while x divided by 2 equals 0, so while x is divisible by 2, I divide it by 2 and I subtract 1 from answer. And then, but clearly if I add 1, might be divisible by if x is if x div 2 yeah, right. Oh god, I still I look at its remainder with all possible powers of 2. So what I'll do is for int j equals 0, for all possible powers of 2, 15, I'll look at x divided by 1 to the j. That's the remainder. And at this point, what I can do is I add the remainder plus I add 15 minus j. I multiply it by 250 minus j times. Come on, what? At 0, wait, is it not 2 to the 15th? Wait, yes it is. to add 1 to the j minus the remainder. No. It's if it's the same, it's 0, otherwise it's if it's remainder, otherwise I add 0. God, I think that should work, but that took way too much time, and it still might be wrong. No, it's accepted. Yeah, that shouldn't have taken that much time. I didn't think. Okay. There are n trees in a park, numbered from 1 to n. The initial height of the ith tree is hi. You want to water these trees, so they'll grow to the same height. Well, you start by watering trees at day 1. During the jth day, you can choose a tree and water it. The day is odd. Then the height of the tree increases by 1 if the day is even, then the height of the tree increases by 2. Okay, well, I need to choose the tallest tree because there's no way I can make the trees shrink. And then each day so I have k odd days and k even days. The number of 2's and 1's that I add to the trees will differ by at most 1. Okay, let's actually draw this one. So it's 2, 5, 4. Let's draw it in order to 2, 3, 4, 5. 2, 3, 4, 4, 5, 7, 8. 2, 3, 4, 4, 5, 7, 8. I need to grow each of these trees to 8. Can I binary search the amount of days I need? Let's say I have exactly j days. That means I add, if j is even, let's say I have 4 days, so that's 1, 2, 4. If I have 4 days, then I have j over 2 1's, j divided by 2 2's. If j is even, so let's say 5, it's 1, 2, 5, I have j divided by 2 plus 1. So this is, of course, like truncated 1's, and I have j over 2 2. Okay, next part of the problem. Can we solve it if I have a 1's and b 2's? And I have an array of differences, so it's like 6, 5, 4, 4, 3, 1. And I need to use my A1's and B2's to make all these numbers. Can I do this greedily? No, I don't think I should. I should no. The 1 must be done with a 1. First of all, if the sum of these, is larger than the sum of these, so if the sum here is larger than a plus 2b, then I can't do it, but I can't definite. And after that, first I have to take all the ones and put the 1 in them, because that I'll definitely have to put the ones in the ones. Then I'm left with some a1s, b2s, and I have some numbers 6, 5, 4, 4, 3, 2, 2. I have some numbers which are all bigger than 1. If their sum is smaller than or equal to a plus 2b, can I always solve it? If I can use up, first I try to use up as many 2's as I can, and then I think I can do this greedily actually. I'll use up as many 2's as I can, and then I see if I can finish right off with the 1's. Yeah. Because the problem comes when I cannot use the 2's. Okay, so I'll just binary search it. That should be easy. That should be easy. That should be, come on. Let's speed on this one. In 16 days I'll have 8 2's, and yeah, let's just check if it actually works. It's not. So here I have this, and I'll have 8 1's and 8 2's. I'll take 3 of the 2's and destroy this. So now I have 5 2's. I'll take 2 of the 2's, and this will be a 1. I'll have 3 2's. I'll destroy this. I'll have 1 2. I'll turn this into a 2. Then I have 1 2 3 4 5 6 7 left, and I destroy those with the 1's. Okay. And I guess I cannot do it for less. Okay. So now I read an end. I read in my heights. I sort. I'll do, and I'll have equals a n minus 1 minus ai. So I'll take the difference for all of these, and then let's do what's the maximum possible number of moves I'll need for the answer. That's like it can be, let's say, like 2 to the 50th. I can definitely solve it with 2 to the 50th. And what I'll try is the largest number so that I cannot solve it. The one after that will be good. So for 100 equals 0, and I like to use a like a binary lifting type binary search. And I have small, long, and my binary search is find the largest number such that I cannot solve it with x, largest number, and such that I cannot solve it with n, and then the answer will be n plus 1. And let's do if because let's say it could be 0, and I have a bool check function how was it? So it's j over 2 ones is j over 2 plus a is x divided by 2 plus x, and b equals x divided by 2. Okay, here if not check, something like that. And for check function, what I do is I'll try to take out this, so for int I equals 0, I smaller than minus 1 plus this side. I'll make a copy of it. Or should I'll put it in some like priority queue. It doesn't really matter, but I don't think that the log factor will really count here. And implementation wise, it's a bit more neat. PQ push while PQ size and PQ top is bigger than or equal to 2. What I do is I div equals 2 if, and then I'll subtract and I have 2 times and b minus idea times. And sum equals 0, PQ size is smaller than or equal to a. Okay, something like that. What's the problem? Oh right, I already have an A, so let's call this H. Let's hope that this is fast enough, or someone will hack it on it. No, I don't think they will. This should be fast enough. Well, that's interesting. Let's try a test case like this. I have 5 trees, 5, 5, 5, 5, 5. Okay, what's the problem? Oh, yes, on test 2. What's the maximum difference? Well, can't have like 10 to the 9th times 3 times 10 to the 5th. That's like 10 to the 14th days at most, right? Okay, am I doing something wrong? Yeah, wait, so what's the... Okay, let's have it like this. I don't know why I wanted to use a priority. Let's first check the code. That doesn't take too much. Wrong answer on test 2. That's interesting. I don't have to... Yeah. I can grow it 1 taller. Okay, well I can solve the problem twice. Okay, that's true. I can do... and I have so first I have mx equals hi minus 1. I increase its height by 1. I think that's the only difference I need to do, and then I'll just solve the problem again. Answer 2. Yeah, because in this case, what I can do is 5, 4, 4, 4, 4, 5, 1, 5, 4, 4, 4, 4, 5, and that will be 6 days. Instead of, let's see what it would be without this. One, 2, 3, 4, 4, 5, and it's 7 days like that. That's not good. Okay. No, it's not worth it to increase the largest one by 2, because then the parity will be the same. What if I increase the largest one by 2? worth it to increase it by... Because I can see why it's worth it to increase by 1, because 4, 4, 4, 4, 4, 5, well in that case it's obviously... I'm not gonna have that many odd days, but if I increase it by 2... So I try to make them all 7. Should I just try increasing it by 2? Did I submit the right solution at all? One plus 1. I go through the numbers. It's max minus hi. That's the difference divided by 2. And I try to subtract 2 as many times as I can. Oh, that's n minus 1 right there. I didn't change that n minus 1. Oh god, please, please let this be the bug. And okay, well, it works the same for this. And that's a very tricky edge case if they got that covered on test case too. Yes. Okay. Well, I guess I'm happy about that, but I still don't think I'm doing very good yet. But E was solved very good, or F was solved very quickly by Rainbow, so I still have some chance. Okay, D. Not many people solving D yet. You are given two arrays, A consisting of n zeros and B consisting of n integers. You can apply the following operation to the array an arbitrary number of times. Choose some subsegment of A of length k and add the arithmetic progression to this subsegment. Okay? So for some numbers in the one that originally contains zeros, I add numbers 1 to k. The chosen subsegment means contiguous, I guess. I can only increase the first element in sets of 1. So I need to do that first. I can add arithmetic progressions on segment trees. Is that the right move here? Because for each element I know how much I can increase it by, and I go from left to right, so I increase the ones, then I increase the next one in 2s. Well, not necessarily, because maybe if I increase it once, then I increase some other thing k by k. I definitely have to increase the first element at least bi number of times. So I need to increase the first element 5 times, that's obvious. after that, it might not be worth it to increase all of them by the most. Well, if by increasing it by 2, I can do it in one move, then it's worth it, right? Because in one move I get that one, but I also increase one that's not. Not sure, not sure. Is there an interesting example? 1, 2, 4, 1, 2, 3. I increase it by, and it's in the 1, 2. Then I go and I increase it 1, 2, 3. Yeah, something like that. First I do 50 increases here. Okay, let's try to solve it for this one. 50, 17, 81. 50, 17, 80, 81, 25, 42, 39, 25, 42, 39, and 96 at the end. First of all, I need to do 50, 50 from the beginning, so that will be 50, 100, 150. First 3 are covered. At this point, I could take the 25s by doing increases here. But I don't think that's worth it. I think it's worth it to do 25 from here. So 25, 50, 75. So far I've done 75 increases. And then I have to do 96 divided by 3. That's 32. That's 107, and that's larger than 92, so I can do it faster. After the initial 50, how many do I have left to increase? I have out of, wait, it's 92, so I have 42 increases. And it's still of length 3. What's 25 divided by 3? What if I increase 25 in 2s? For the 96, I need 32 at least. So I do 32, 64, 96, and I have 10 left. I do 8 increases from here and 2 from here, right? And that's not going to be enough. If I do 8 times 3, that's 24. What if I do not 8 but 6 increases from here and 4 from here? If I increase 6 from here, then I'll add 6 times 4, no, 6 times 3 plus 4 times 2, which is 26 here, and I'll add 4 times 3 to here, which is 12. Okay, so that's not obvious. It's not obvious why that would be correct exactly. So let's just write down how many progressions I start from each position. From here I start 50, 6 I start 4, I start 32. And that seems to work. How many numbers? It's a tentative. Because for each position, so let's say here, I know it's 3 times 6 plus 2 times 4. For this position, I know it's 4 times 3 plus 32, 4 times 3 plus 32, which is 44. Here I know it's 2 times 32, 3 times 32. Here this is going to be the biggest one because it's 3 times 50 plus 2 times 6 plus 4. It's 166. So this is what the construction for the correct answer will look like, I guess. It's going to be something like an array of numbers whose sum needs to be minimal and which solves the problem. What's the minimum to solve 42 with 3 is 42 divided by 3, then I would put 14 here and that doesn't work. I had arithmetic progression. I'm adding these arithmetic progressions. Yeah, I'll get some water. I think I forgot to unpause the recording. I think I have a solution for these. So what I've realized that it's always optimal to take the rightmost position and subtract from the furthest away point as I can. So optimally I subtract k until the rightmost position is positive, and then I go to the left. And that should always be optimal. And now I'm thinking of how to execute this. I could use some sort of segment tree, but I think it should be easier than that. Might not be. If I subtract k from there. a segment. I'll just use a segment tree, but I don't think I'll. Yeah, this is the point where I don't think I'm gonna code it. I'll just take some of my old code. I think that's fair. That's fair. I mean, that's not cheating. I just don't really know how I would code it right now. Arithmetic progression on segment. Let's do submissions. What's the problem? I'll figure it out. Modify range AV. So A and V is the step, I guess. I can do position value and modify range. Okay, that should be very helpful. Let's duplicate the step. Let's take this step and put it on my second monitor. Okay, now I have n and k. I make a segment tree of size n, and I also have vector int b, and that's long, and also have the segment tree store longs. It does store longs, okay. There are n items in my segment tree. This is like very old segment tree code, but it's definitely works. And what I do is I have ans equals 0 for at position I. Wait, did I? No, I didn't read in B. Read in B. I have the position value of I if V is smaller than what's the largest number I can subtract from BI or from oh yeah, let's subtract BI, so add to V from position I. Well, it's minimum of k and I plus 1. It's minimum of k and I plus 1. And then I'll get equals bi minus v plus most minus 1 divided by most times I need to add this. And now I do I increase by time, modify range. I go I minus most I, starting from 1 all of the. I always start from 1 and I have a step of 1. try for the first one. Not correct. Wait, is it one less for each of them? No. Okay. Now it uses 6 moves for some reason. I equals and I should look at what this was. So yeah, this should work. So first of all, I have most is equal to 3 and go to 6. Oh, it's times and yeah, 5, 3, 3. Yeah, I think that's accepted. That's accepted. So what does this code do exactly? Yeah, I can calculate the sum for the left and the right, and I can add two halves of two arithmetic progressions. But I'll look over this code because it definitely would take me another 20 minutes to code this if this wasn't already like prepared. So now I'm getting in a better territory. Let's look at E and F. I think I'll read both of them this time. Because F took Rainbow at like 40 minutes and E took an additional 30 minutes, so means that F is probably more standard, right? Okay, problem E. A matrix A consisting of 3 rows and columns. Each cell of the matrix is either free or taken. So 3 rows and columns. So it's like a very, very long rectangle. A free cell Y is reachable from a free cell X if at least one of these conditions hold. X and Y share a side. There exists a free cell Z such that Z is reachable from X and Y is reachable from such that Z or Z reachable from X and Y is reachable from Z. So all of them are reachable from each other. No, because there are some taken cells, okay. But they are, so this is essentially they are reachable. Yeah, this is just complicatedly saying that this is a complicated way of saying that you can move in free cells, and a connected component is a set of free cells of the matrix such that all cells are reachable from one another by adding on any other free cell to the set violates this rule. Okay, yeah, that makes sense. So that's just the connected components in this graph. You are asked Q queries about the matrix. Each query is the following. LR, count the number of connected components of the matrix consisting of columns from L to R of the matrix A inclusive. 2, 3, 4, 5, 6, 7. What could happen is, okay, I think I'll think about that for like 5 minutes, and then if I think it's very hard, so what could happen is I have a free cell here, a free cell here, that's not, and then after this all of these are free, but I cut it off from here, so these two are free. Can I do this with some sort of like Mohs algorithm? There's this technique with disjoint set union rollbacks, which I don't know how it works, but maybe that's what I need here. Well, I'll do the queries offline anyway. I start for each point in left. Let's go from right to left, and when I reach a new state in left, well, I just connect all these disjoint set unions. Okay. So I move from right to left, and I slowly connect these. So I put in this line. Then I put in this line with what's the 0 or 1s are the free cells. That's 1, 2, 3, 4, 5, 6, 7, and 7 evenly. So first I reach this row. Then I reach this row. then I reach this. So I can answer all queries from N to L. Can I put these in some like segment tree and answer the queries from R to L? So when I have these numbers, yeah, I have it. One, 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 zero. Let's do 1, 1, 1, 1, 1, 0. Let's say I've processed it up to here, and I take a slice like right here. I need to have there's gonna be like top components, bottom components, and connecting components. But that, let's say that was no. Say that was connected to the number of components in here will be, well, I take the number of components here, which is 1. I take the number of components in total, which is 2. I subtract 1, and then I add some number. If there's a component, there can be 2 components that reach over. So what can happen is 1, 1, 1, 1, 1, 1, 1, 1, 1, and 0, 0, 0, 0, 0. Here it's 2 minus 2. The number of components that cross this line. This and this. What if this segment tree is like persistent? These two are already what I can do is I check it from here to the end. And here to the end I store what would I store? I store like the number of components. I store, no, that doesn't work at all. No, I don't know yet. Some people are solving it, not many. Yeah, I'm in a bit of a plus now, but it's pretty small. It's like what does this 3 times n mean? It means that my components can't look that, so can have something. If I have something along the bottom that's like 1, 1, 1, 1, 1, then I have some zeros. These graphs that I have here are bipartite. That's cool. Here it would actually be just a tree. So the only problem that I have, let's see what would happen if we only have 2 rows. With 2 rows, I can just have, I check the number of components up to L. And I check the number of components up to R, so number of components up to L, 1, 2, 3, 4. Let's do 5, 6, and I subtract the number to R, to 3, minus 3, and I add the number of components that cross, which is equal to 6 minus 3 plus 1, that's 4. So it's 1, 2, 3, 4. Yeah, okay, that's correct. What do I do when there's 3 rows? So here I add the number of components from left, that's 1, 2. That's 2 components. I subtract the number from here, that's 1. Now, and this is the tricky part, what I do for each component that runs on 2 sides, I store, so I put these in like a disjoint set union, and I store the latest bridge. So for this component, the latest bridge will be, let's do 1, 2, will be at 4. So it's 2 minus 1. Then I check these two and I look at the number of components that connect. So I do 1, 2. Here it's either 0, 1 or 2. It's 2 if it's 1, 0, 1 on here, and these, so if these match, it's 2. Otherwise it's 1. So I add 2. I need 1, 2, 3 at the end. So I'm good right now. No, I look at the latest bridge. So when checking the neighborings of these two, I look at 2 things. So what could they look like? It could be 1, 0, 1, 1, 0, 1. Look at which component, well, these two will be in the same component, definitely these two. I look at the components of these two. if the latest bridge in these two is after R, so it's somewhere here, then I add 1. If the latest bridge between these two components, if these two aren't in the same component, then I don't add anything. If the middle matches the middle and nothing else matches, let's say middle matches middle, top matches top, I need to look how many components are crossing the border. Because in the case of this, there's clearly one component crossing the border which has been subtracted from the right side. Need to look at the number of components crossing the border, so when we look at the border from the side that's still in, these two, if they cross the border, they need to be counted separately, because if these two are connected here, okay, I'm getting somewhere. I think this might be possible. So I store the latest connection of these two. Okay, and what do I do next? If the middle is on, this can be either 0 or 1, this could be either 0 or 1, and if the middle two are connected, then there's one component crossing the border. So if mid equals 0, 1, then it's going to be L minus R plus 1. So let's do an example for that. That's 1, 1, 0, 0, 1, 1, 0. And if it's from here to here, well, it's 1, 2, 3 minus 1 plus 1. Oh, that's if mid equals 1 for both of them. If middle equals 1 for both of them, then I know there's a crossing. If, so else, mid equals 0, mid is blocked, then I can have one on the top and one on the bottom. So there's either a crossing on the top, and there could be a crossing on the top, and there could be a crossing on the bottom. 0. If only top or only bottom, then I'll add 1. There's 1 crossing. And then if there's top and bottom, what? In that case, I need to look. So first of all, I need to look if they're in different disjoint set unions. If diff DSU, then 2 crossing. If same DSU, then either last bridge after R, then it's 1, otherwise, else there's 2. I think that should work. 22 minutes. Okay, challenge accepted. And what I have is some I store the number of components from n to some point. There's going to be at most 3 times n components. I to p of n I don't need the size of component, I just need I need last bridge, and I need the number of components in total. Do is for int I equals to -1. I have a queries of n. And I store this as m. Q of L, Ri, and I have some answer of n. I need something like that. With n. Now what I do is I add the new components. If s some. ID of Ji equals if no, and then if IDJ is 0 I and ID I no, the count isn't good. Two, then unite 1 and 2. Zero I and I need to make int I into I think I built my graph correctly. Then now for int auto RID if R equals n-1, answer of ID equals and continue, else ans of I equals no ID count minus comps of r plus 1. And now I need to do my, I think I'll put this on my other screen too, and then I can look at it. Okay. If id 0, and then I look at the two positions. Where is the crossing? Well, it's at positions r and r plus 1. There's a crossing, then there's no crossing in the middle. Bool top equals 0, bot equals 0. And then id r 0 and id r 0. If there's top and bottom, else this equals top plus bot, and I'll put these as integers. And this is the case when there's only top or only bottom or none. There's none, of course, then we don't. There's no crossing. And now I look at the if, so there's crossing on the top and the bottom. Top equals find id r0 equals find id r2. If top equals bottom, if it does not equal bottom, then there are two crossings. If last bridge parent of u equals v, last bridge of v equals minimum of last u last bridge last bridge of top is smaller than or equal to r, then and this is ons id. It's and here I need to write id 2. 2. This could be probably done much faster. ID of, and here it's also 1. Yeah, that's weird. Why do that? Okay. Not completely correct. For each turn, count is 2, count is 3. It should still be free. Alright, because I unite those and I also need to unite. And I also need to unite that 0 if there's a 1 and 0. And there's 1 that's wrong. The 1, 2, 3, 4, 5th query. The 5th query is 1, 5, 8 to 11. So the 1, 2, 3, 4, 5th. 1, 2, 3, 4, 5, 8 to 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So there is 1 component. Count for, so that's 7 to 10. Count for 7 is free. Why? 1, 2, 3. What's n? N is 12. S. Comps are +1 bit. Here I should. And ID2 equals to, should be the 5th, right? 0, 1, 2, 3, 4 equals 1. Right. And what was the problem? Oh god, I had like 1 minute. Quickly figure this out. There's a crossing in the middle, then I increase answer by 1. If there's a crossing at the top or a crossing at the bottom, oh, it's r plus 1, r plus 1. Okay. Submit it quickly. What? Why? Runtime error on test 1. Am I using too much memory? 4, 5. What causes my runtime error? Still runtime error on test 1. Oh, come on. Oh, wait. Okay, wrong answer on test 6. I'm happier with that than the runtime error. Oh. Wrong answer on test 6. Why? Yeah, I'll go over the solutions in a bit. I just need to. Can I look at the test? Not yet. I think I can look at the test now, right? Not yet. I'll just quickly run over the solution again and try to check if there's anything I can find that's wrong with it. There's top and bottom. Then I do bottom find to r. Top does not equal bottom. Yeah, I think that should work. The last thing I'll need to check is how the last bridge is handled. Well, if I is a bridge, then last bridge of find id 0I will be equal to I. If I unite two elements, It's the minimum of the two last bridges. One, two. And when I make a successful union, I subtract that. Yes, that should be. Wait, what if I need to put M here? That might be it. Oh my. Oh, okay, good, good. I'm actually happy with that. I would have been annoyed if that was it. I've just spent like 30 minutes debugging my code for E, and I finally found the case where my solution is incorrect, and it's not it's not a bug in the code, it's actually the whole solution is incorrect for one case. So I'll leave that and I'll solve that later. For now, I'll explain problems A through D, and I'll try to do this as quickly as I can. Problem A, we could swap, so we were given two arrays, A1, A1, A2, A3, and B1, B3, Bn. What we could do is swap two elements that are above each other, so AI with Bi, and we wanted to minimize the sum of the absolute differences between each neighboring elements of both arrays. Here basically what we needed to realize is that we can always achieve the minimum. So let's say that we have some AI plus 1, Bi plus 1. If the absolute difference between this and the sum of those is smaller than the absolute difference between this and this, then we swap the two elements. And it's going to be AI, Bi plus 1, Bi, AI plus 1. And for the next position, if the absolute sum of these two is bigger than the absolute sum of these two, well then we'll just swap the next two elements. So we can always get the optimal answer by swapping the next two elements when we need to. And here this way it's always for each pair of neighboring elements, it's always the minimum of swapping and not swapping. Problem B. So we were given an integer v, and we could either increase it by 1 or multiply it by 2. And we always take modulo 2 to the 15th. And we needed to find the number of moves to make all elements in AI 0. Well, we can do a couple of things. We can, first of all, if x is, so we need to make v, or we're going to v, divisible by 2 to the 15th. Well, if v is, let's say, divisible by v is divisible by 2 to the 13th, well, then multiplying it by 2 twice, we're gonna make it be divisible by 2 to the 15th. That's the first thing we need to notice. And if v gives some remainder, so if v modulo 2 to the 13th, and this is 2 to the 13th minus v modulo 2 to the 13th, so the difference between its remainder and the number, if we take this difference and increase v by this, then v will be divisible by 2 to the 13th. Because it gives this modulo, and we need to increase it by this much to have v be divisible by 2 to the 13th, unless v divided by 2 to the 13th is 0, because then we need to add 0. And this way we can sort of like check for each power of 2. For each power of 2, what we can do is we increase v one by one until v is divisible by 2 to the jth, and then we multiply v by 2 15 minus j times. And this is just the code for that. So for each remainder, we check what the remainder is. We add, we increase it by once until it's divisible by 2 to the jth, and then we add 15 minus j, because that's the number of times we multiplied by 2. Okay. For problem C was a bit more tricky. In problem C, we were given some trees. What was a good example? Let's do the, I'll sort it in increasing order, because the order doesn't really make a difference. So 2, 3, 4, 4, 5, 7, 8. 2, 3, 4, 4, 5, 7, 8. And here I solved this with binary search. I fixed the size of the largest tree. So the problem was we had to increase the trees. These are the heights of the trees, and we had to increase the trees through some given operations, such that the sum, such that all the trees have the same height at the end. Since we cannot decrease the height of the trees, this final height will be at least as tall as the tallest tree in the group. And the second rule was that on all odd days we can increase one tree by 1, and on all even days we can increase one tree by 2, or we can for all days we can just skip that day. First of all, what we need to realize is that if I can solve it with x days, then I can definitely solve it with x plus some number y days, where y is a positive integer, because I solve it in x days, and then for the rest of the y days I do nothing. So this function is monotonic, which means we can binary search it. So we can find the largest x for which this problem is solvable. The way we check for an x is we know if there are x days, then x over 2 plus x divided by 2 will be 1s, and x over 2 will be 2s. This is all, of course, truncated. We take the remainders from the tallest tree. So first we're going to try to make all of the trees as tall as the tallest tree. we take the differences, so that's 6, 5, 4, 4, 3, 1. And first we try to use up all of our 2's, because the 2's cannot be used everywhere. So we use up 3 2's in the 6, we use up 2 2's in the 5. I don't know how many 2's we have because we haven't fixed x. And then we take the sum of the elements that remain and we try to fill them up with the 1's. The main problem that will appear is some test case like this, where all the differences are 1's. So all of the days that we have must be odd days. So for this we need to have at least 8 days because we need 4 odd days, or at least 7 days. Because of this, we also need to check the answer if we make the final tree height be 1 larger than the last tree. So we also find the answer if the last tree is increased to 9. And in that case too, we binary search it. I'll show my binary search function. So, well, at least the check function. I go through all the trees. I take the difference between mx, or that's the max height of the tree. At the beginning it's the last tree. For the second turn is the last tree increased by 1. I'll subtract 2 from them as many times as possible, as long as I have some 2's left. At the end I take the sum of the remaining heights, and if that's smaller than a, and a stores the number of 1's I have, then I can solve it for that x. I just binary search for both possible maximum heights, and I print out the minimum of the 2. Okay, problem D. Problem D was, I don't know, it wasn't very interesting, it was sort of interesting. We were given an array that contains zeros and an array B consisting of integers, which could be pretty large. And we can do an operation where we select a sequence in A, some segment of exactly length k, and add an arithmetic progression to this subsequence, subsegment, so contiguous subsegment of A. And we add the arithmetic progression of 1, 2, 3, 4, 5, k. And we have to find the minimum number of moves to make A equal to B. There's a greedy solution to this, which uses the fact, and I'll try to draw this, but I won't remember the numbers. Okay, let's put it here, and then that's very smart, I think. So that's 50, 17, 81, 25, 42, 39, 96. We need to prove that it's always optimal to take the last number and remove it or increase the last number in AI. It's the same if we try to decrease the numbers in B in the least number of moves. So if k equals 3, then we need to have enough progression starting from here. So from this is position I, this is I minus 3, starting from I minus 2, such that the last position will be removed. And this can be done in 96 divided by 3 moves, rounded up. This is true because, well, let's like try to find a contradiction. So let's assume that this is not true, so it's better to remove it in this fashion. Well, in this case, I'm gonna take more turns to remove 96, which is first of all bad, but it could be good because let's say that for another number before 96 I remove more from it, so later we have to make less moves, but that's not true either because I take more moves to remove 96 and I subtract less numbers from each number in the array when doing moves like this. So it's always optimal to remove the last one. And after we have this like greedy idea, we just need to implement this, and there's a way to increase a range in a segment tree with an arithmetic progression. I don't completely remember how it's done, but I know I solved it like a couple of years ago, so I just pasted in that code. And what I do is I find the furthest position from which I can remove the last number, and I just add the arithmetic progression. Yeah. Problem E, I like problem E a lot, but my solution was incorrect at the end. I will be up solving that. Okay. But yeah, this was a fun round, I think. Thanks for watching.